The final presentation of today's session is in charge of Le. Le did her PhD in Glasgow, working on the probabilistic effects of unsaturated solid mechanics, and currently she's on the onshore division of geotechnical engineering at NGI, the Norwegian Geotechnical Institute. While the presentation loads, please remember that tomorrow we continue with these sessions. We will start sharp at 9 a.m. So please arrive on time. And Le, the floor is yours. Thank you.
Thank you, Miguel, and thank you for the introductions. Now it's very late, so good afternoon. But I know it's been a very, very long day, so I try to make this as fast as possible and as simple as possible. I'm not a professor. You see, the rest, all the ones that have speak today is professor, so they make things very complicated. But I will just take you through how you're going to go from the centrifuge and then the test pits, which is in the lab, to the field, which is basically realities, as close to reality as you could. Yes, actually, I have to mention the presentations is actually prepared by Stephen Bayton. He has a lot of experience in PI testing and offshore, so it's more offshore oriented, which is different from what I'm working on. And I'm sure by now you are much better at PI design than I am. So you will have question on that. I will ask someone here to help you, but I could certainly answer a question related to field testing if you have any at the end. Now, the presentations will include some introductions on field about field scale testing, how we do planning if we want to do field tests. Site investigations is very important, actuations and data collections, and the end, an example through a case study that we've conducted at NGI. Now, what does it mean to test at a field scale? As standard, it means to perform a large-scale physical modeling of a geotechnical problem in test conditions that are more realistic of the in-situ conditions. And what that really means is that the realistic of the in-situ condition, it means we test this in naturally deposited soil, as opposed to what you've seen all days, where the sand is actually prepared, that is done in the real environment, operational environment. It is close to real scale, which means it's in case of PI, especially for offshore wind turbine, it can be really large, as you can see in the example later. And it replicates installations methods in the way that is as realistic as possible. But why do we not test in a centrifuge or large-scale laboratory as you've learned so far? It's because in some cases, it's simply not possible to reduce the scale of the models, prototype design, or new tools. And also the in-situ condition at the location of geotechnical problem may be unreplicable in a used prepared model. And this is actually maybe the main reason for this, because reality is soil is very, real soil is very, in natural environment is often very complex with layers, structures, fabrics, with deposition and stress histories. It's not easy to sample to prepare it in the test pit or in a centrifuge, and it's very easy to disturb, which change its characteristic completely when you test. And of course, scale effects, I'm sure you have learned a lot about it today, and rate effects in observed at the field scale. The field scale test result can have a wider impact on industrial practice. And some couple geotechnical processes do not scale perfectly anyway. But why don't we just do field scale tests and not doing lab tests then? The main reason is extremely expensive, and it is the reason for many things why we don't do it. It's time consuming. It's you can have a quite limited test matrix compared with what you can do in a centrifuge or in a test pit. It have repeatability difficulties, of course, also because it's expensive, and the condition is natural. We have a much less control than if you test in the lab. And in situ condition can be very complex to allow full understanding of governing parameters and mechanisms. Some example of field scale testing that we perform at NGI, for example, laterally loaded pipe. We also test new tools and new sampling methods, new type of CPT, DMT, all sort of things. Vertically loaded piles, excavations, and embankment, where we build almost full-scale embankment to test it. The first step in field scale testing is planning, and it is extremely important. We have to be able to identify a suitable site. Either it is a natural site that have a soil condition close to the operation environment later that you want to work on, or a test site. In NGI, we have 5 different test sites for different soil conditions. And well, I can talk about advantage of the test site when we come to an example later, but so it could be both, either a site that designed specifically for field scale tests, or it's just a natural site that you pick, that you know and could perform the test. And then we have to perform field site investigations, and this is where the difference come in. In a site that designed for field scale tests, like those sites that we have at NGI, then you know the soil conditions. We've already investigated them, so you save costs in terms of field investigations. But if you go to a natural site where you don't have this information, then site investigation would be the first step. And as you can see here, the advantage of a benchmark site is that it saves time and money, because field investigation can be very expensive and it takes a lot of time. And then you have a model structures, instrumentations, model structure fabrics, sensor calibrations, model structure installations. You have to have an installation contractor, because it is not simply a small model that you could do yourself. Normally it's involve complex equipment and high cost. And then you have to have actuation measurement devices, a pre-test study to identify the required applied force, length of LVDT, etc. And then a test program in the end, once you have this information in hand. And at the end, you can't just leave the pipe there. You have to take it out, decommissioning. Yes, I see how I go with time. Site investigations is very important, and it is important in realities when you actually, hopefully one day, work as a technical engineer. That is the first step, and this very important step, because it gives you information of what you are working with, what you are designing for. In this case of field testing, basically the sample have been created naturally, and we do not have full control of its properties, so we have to find out what it is. And soil have been placed, compacted, and restructured naturally over thousands of years, as opposed to, as you see in the centrifuge and in the test pit, it is man-made in a way. As the figure show here, that's how you prepare the sand in the centrifuge, as opposed to in the natural environment, where soil go through many cycles of erosions, depositions, compactions, uplifting, etc., etc. And if you do CPTs, as it shown here, you can show that it have layer, it have a different fabrics, and it have different material at different depth, and it vary spatially. Also, this another similar example, how you consolidate it in this for centrifuge testing, as opposed to the consolidations process, which a natural soil object subjected to, which is a lot of cycle retreating, advancing by ice, and natural deposition environment. The reason for site investigation then is clear. We need to learn as much as possible about the site where we perform to plan the field tests. to allow the best understanding of soil conditions, accurate back analysis and comparisons, and have to explain unexpected results from your field test. This is an example of a benchmark test site, a sand site in Norway that we use to test, to perform tests when we wish to test in sand. It's a part of a project we call Norwegian Geotest Site. And it therefore have undergone extensive site investigation. Basically, it's outdoor lab. We know where the water table is, what's the soil condition, what's the grain site conditions. We have done hundreds of tests at these sites. And if you actually go there and install a PI, you could skip the part about soil investigation. You can just start from designing the test. As you can see here, this is just an example where we have performed different type of tests. And also a lot of tests are using geophysics method to classify it between the boreholes, to fill in the information between the boreholes. Yes, we have also done various CPTs at this site. This is just an example of it. So we know the shear strength, both shear strength wells and poor water conditions. And yes, as you can see, soil naturally vary. Different color here we show different CPT at different locations at the site, and it's not it's as homogeneous as it can be, but it's still quite different from locations to locations. And then also, this is just as example, because we've done a lot more tests than this, but just so you have a kind of appreciation for that, natural soil is completely different from prepared soil in the labs. It is an example of hydrostatic water levels, and it's not constant. It have also seasonal fluctuations to be aware of, and also you need to be careful for suction pressure above the hydrostatic or water tables, because it can influence the results. So the point here is not go to the detailed technical here, but to kind of raise awareness that field condition is completely different, or reality is completely different from what you see in the lab or the test bits. And then actuation and data collections. You have a very large model in this case. In the field, normally it's very large models. And you also must then have equally large reaction frames. As you can see here, it's a model of a test of 2 piles, and this is realities, how large this is. In this case, they perform lateral loadings in pairs, so they could perform 2 tests for the 2 tests at the same time. And then this is a loading frame to test vertical loading for reactions, resistance, and pull-out capacities, a PI test in the field. And another issue is large models also generate very large displacements. And which means that it's not so easy to, we don't have a test bed boundary frame for displacement reference. And we have to create our own reference points. As you can see in these figures, they have put in here a frame leg outside the zone of influence by the test in order to have a reference point. And that is how it looks in realities. Additional reaction frames were put in for measuring devices for PI tests in the field. And then other complications include rotations. In this case, large rotation and displacement sensor need to be corrected for interpreting displacement data. Yes, on that is just to give an example of how complex it can become for field scale testing. As you can see, it's complex in the lab and in the test piece, but it's even more so in the field. And now is the last part, which I will go through, is an example of a case study, Dutch wind farm, where they want to install monopile in very hard clay with underend shear strengths of over 1,000 kPa. It is extremely hard. And in this case, it is too hard that there's very high risk of driving refusal. And that was the motivation for field scale testing in this case. As you can see, they want to find a method to reduce high driving resistance expected in hard to very hard clays, where they try to drive the pile in, but it didn't reach the target depth before it being refused. And then the question is, how can we reduce friction accumulate along the length of the piles as the driving progresses? And the solution that they would be able to, they want to test or they want to find out if it works is to place driving shoes both inside and outside at the tip of the monopile, as you can see in the pictures here, in order to provide an oversized hole for following pile shaft and reduce pile frictions. So both inside, outside were basically increased thickness. That is a driving shoes and increased toe resistance, but it's increased toe resistance. But then it reduced side frictions due to the increase in these areas. So the goals of these campaigns were to reduce installation resistance and ultimately reduce risks of pile refusions. But potentially, does the methods that they come up with can reduce lateral performance? And this is the questions that they want to get the answer from the field tests. First, they identify a suitable site. In this case, it will carry out in Rødby in Denmark in 2014. And the reason this site were chosen is because the site had similar soil conditions to those identified offshore, where the wind turbine is going to be installed. And then they have a proposed setup in order to test it. They have a best, and this is a proposed setup. This is the first step that we were talking about before. So we have gone through the first step, identify the suitable size, and then the next step is site investigations. They put down 6 boreholes, 6 CPT, 2 boreholes. In the borehole, you take sample and test it in the lab. In the CPT is mostly to find out about the shear strength. And that is a result that they got back from the CPT, as well as the sample that is tested at NGI and also at the Ferment projects, probably a partner in the project. CPT were to 10-meter depth, triaxial test, both compression and extensions were performed. And then they could, from the soil investigations, they could come up with a best estimate underend shear strength profile, as you can see here. Very simple. Next step is then model pile fabrications, model pile instrumentations, and sensor calibrations. As you can see in this figure here, it is how it looks in realities. The pile have a diameter of 1.22 meter, thickness of 22 millimeter, and strange gouges were installed inside the pile in seven pairs, and also in clinometer. Fabrications, we show in the figures. The installation is done by hydraulic hammer. Strain gauge recording at high frequency to allow the back analysis of installations. And then actuation mechanisms is shown in the figure here, which include displacement laser, inclinometer, displacement extensometer. And then design methods is, for now, in reality, we're still using quite basic design method with charge from the AT or something. well, 64 in this case, we charged, as you can you can see in these figures. And I remember from yesterday's presentation, I think the main reason is time. Often there's, in reality, there are very high pressures from clients to do the project fast. So in reality, we still use very basic design methods in order to design pilot. And then set up a test program. In this case, is the test matrix, as you can see here, with the constant inside shoes and inside shoe thickness and inside shoe length. But outside shoes thickness varies. And testing include two-stage installations and lateral loading. Then the results, as you can see, 6 different pi were tested, with different number of blow, kilonewton meter per blow. And they give different number of blows per 25 centimeter, which shows the effect of driving shoe on installations resistance. And in this case, it showed that the largest driving shoes has the lowest blow count. So it actually helped with the installations process as they hope for. Driving shoes, in terms of driving shoes on lateral resistance, the results will vary between different R&D ratios. In this case, for the 6.1 is not much difference. And particularly, they have an identical load displacement response. So no adverse effect of the shoes, as they concluded. That is for another R&Ds, the estimation and motor failure is a bit different, but also they have identical load displacement response. And the conclusions from the study is that the use of internal and external driving shoes resulted in 25% reduction in total skin friction during offshore installations, and no refusal of the monopile in when they actually install the pie in reality in the projects. So that's it, and the conclusions, just 3 points on field testing. Field testing is necessary to investigate innovative and creative solutions in operational environments. It is actually a required step in many cases where your designs become unrealistic. You could use field testing to kind of pitch the design, change the design a bit, where it not follow or use a more non-standard methods. But proper understanding of field conditions and good planning is a key for successful and useful field experiments. And it's important to kind of integrate between small-scale centrifuge tests, medium, large-scale lab tests, and field tests to bring more research advances to practical applications. And that's it from me. Thank you. Right on time. Yes. Any questions? Everyone is very tired, so we could go. Yes? You want to say something? You want to say something, like announce something for tomorrow? For me, it's, I finished for today, so. Okay, yeah, so you come back tomorrow. I'm going home, but you come back here tomorrow and learn more. And good luck with your study further. Yes. Yes.
So thank you all for coming again. And as it was said, we continue tomorrow. And we see each other here at 9 a.m. And I believe if some of you use the ETH link, the bus, it runs, the last one goes at 45, isn't it? 54, okay. But if you run, you can get the one. Yeah.